Okay, good morning. This is the Western Automation Monday morning technical class, and we are recording. Today we're going to talk about I think, a very interesting subject, and it's even more interesting based on the trip that I took a couple of weeks ago down to a town called Tula de Allende in Mexico. It's about 50 miles north of the international airport in Mexico City. And it is a gigantic refinery next to a small town that is basically there for the refinery. Pemex, Petroleum Mexico, owns the refinery. We were in a new construction section where they were building something called a decoker. And that facility was run by Ecafluor. We were there at the behest of one of our customers, Flowserve, who had built the actual decoking equipment. So the reason I'm bringing this up is that the subject that we're talking about today, which is VFD duty cable, and in more general terms, the conditions on the output of the VFD going to the motor, that circuit, those motor leads, are referred to as a tank circuit. So a tank circuit, if you Google it, I'm going to Google it right now after I share my screen. So please confirm for me, can you see that screen, and do you see drive flex?
Yes, we do.
Thank you. Okay. So I'm going to just, for the sake of this class, and you can do this, tank circuit. And it says a tank circuit is an LC circuit, also called a resonant circuit, tank circuit, tuned circuit, an electrical circuit consisting of an inductor, like the motor winding, or the cables. Cables have inductance as well, represented by the letter L, and a capacitor represented by the letter C, connected together. Now, is there a capacitor in the output circuit of the VFD going to the motor? If you put one out there phase to phase, the drive will immediately current trip, OC trip. And if you're unlucky, you'll blow up a transistor. Not so much on your Scouts drive, because we are fault trip before component failure, but on some of the less expensive drives, you'll blow an output transistor. So there's no capacitor per se on the output of the drive, but there is capacitance in the cables as well. So the tank circuit is an inductive capacitance circuit. Depending on those values, by the way, the inductance of the cable depends on the length of the cable, as does the capacitance to a certain extent, but more so the inductance. So you can set up certain resonances in this circuit, sometimes bad resonances, as I'll show you in a minute. And stuff like this can happen to your voltage on the output. This is not what we want to see. So a tank circuit, basic concept required for the class today, simply any circuit that has some inductance and capacitance in it. Now, let's talk about inductance and capacitance, and we're going to let the Litzer guys do this. By the way, there's Chris Keller, who apparently has internet problems at his house in Phoenix. Chris works for Western Automation. He's our man on the ground in Arizona, and a very capable individual, I must say. Chris, if you didn't know it, used to work for Lutze. We will get back to him. Actually, let's play that video since he looks so good there.
Pierce, I don't think the audio is coming through.
Okay, thank you. We'll stop that, and I know why. It's a mistake I often make, because when you do when you share on Teams, for some reason, there's a little button switch on the right-hand side that I've now activated that includes the sound, but it's not default. Thank you, Wyatt. Appreciate that. We'll start the video again.
Which now, I don't know if you're sharing this. Did you start it already?
Ay, ay, ay. Yeah, I did. It says share.
Maybe I'm just not seeing it.
Oh, somebody else pipe in.
I'm not seeing anything either.
Okay, Kevin, thank you for that. I'm going to unshare and start this all over again. Include sound. How about now?
Yeah, we see it. Let's see if we could hear it.
Oh, well, you'll hear it in a second because I'm going to start it over.
Yeah, perfect.
Hello and welcome to the Lutze video series. My name is Chris Keller.
And I'm Matt Tarney. We're product market managers for Lutze USA. Today we're here to talk about our DriveFlex product line. DriveFlex cable has been specifically designed for applications using variable frequency drives.
Exactly, that's right. The cable helps to mitigate the electrical challenges created by the VFD.
It's no secret that VFDs introduce a lot of noise into your system. DriveFlex has been specifically designed with braid and foil shielding to combat this harmful electrical noise.
It's also known that VFD applications create a lot of high voltage spiking. Therefore, we use an XLPE insulation on the conductor that helps to cope with those spikes. The XLPE material offers great electrical values and voltage breakthrough resistance.
In addition, DriveFlex is the most flexible drive cable on the market. This flexibility allows for fast and easy installation, even in applications that have tight bending radii.
All Lutze DriveFlex products are UL listed for the intended use between a VFD and a VFD motor. They're also listed as power tray cable.
Depending on the model you select, DriveFlex has a variety of other listings that covers a broad range of applications.
When it comes to VFD and motor supply cable, there's no room for compromise. Lutze DriveFlex offers a safe wiring method for all of your VFD and motor cable needs.
Thank you for watching our video today. For more information on DriveFlex and VFD cable, please view the other videos in our series, visit us at www.driveflex.com, or contact your local Lutze representative.
Now, I'm going to play those other videos, and I want to point something out to you here. So, this is
Variable frequency drives.
that's Fedority. Yeah. Drop it down. I just want to point out this configuration to you, because I really like this cable configuration for variable frequency drives. Note the 3 conductors, and these are the ground conductors nested amongst the 3 conductors. Lutze cable, and other manufacturers of VFD cable have come up with this design for a couple of reasons. First, the cross-section of the ground conductors combined, because you join these at both ends, are code compliant. So you have enough ground conductor here amongst these three to equal a normally configured cable. But note the difference in geometry between this side and this side. VFDs, because of their pulsating output, create common mode noise. This is the common, or the ground in this case. Common doesn't always need to be ground. In some circuits, it's floating. In the VFD circuit on the power end, it's ground. Now, this pulsation effect creates noise on the ground. You don't want noise on the ground. Your ground's supposed to be zero. When it bounces up and down, think about what that does to your control circuits that are referencing ground. They now start to bounce up and down. So, this geometric configuration causes additional cancellation of this noise because of the geometry. Therefore, this is, from a noise standpoint, superior to this. This also allows the cable to be a smaller diameter and thus more flexible. So in the installation and cost of installation, cost of handling standpoint, it is superior. Also, note in all of these cables, note how finely stranded these cables are. Another very, very important aspect of VFD duty cable. This fine stranding means there's more surface area on the individual conductors when you sum it all up versus thicker conductors in here. High frequency noise tends to travel on the surface of the conductor. You want an easy path for that noise to sink down to ground, so it doesn't start bouncing around and affecting other things, creating capacitive discharge, etc., which we'll talk about in a second. The higher the surface area, the more finely stranded the cable is, the higher your chances are that you're going to sink your higher frequency noise to ground. That high stranded cable also is very flexible, thus Drive Flex is the model name that Lissa uses, and several of the other VFD cable manufacturers use Flex in their names for their models. We used to call this welding cable. This is a very flexible cable. This is a pretty beefy piece of cable. If it was normal THHN, you couldn't bend it. But this one easily bends. Again, we're talking about advantages here versus standard cable for the VFD application. I want to talk a little bit on why we even bother. And frankly, most people don't bother, and in this country especially. And that's a real problem. It causes a lot of troubleshooting at the installation end of the game that just doesn't need to happen because our practices are not best practices. So, why? Well, THHN and some of the other standard cable types have been used forever, and the justification is, well, I've always used that and I haven't had any problems. But now you're putting a VFD in here instead of a contactor, and that changes the waveform going down the cable. So is it not logical to think that we might want to alter the cable characteristics so that we can ameliorate some of the effects of the new waveform? The new waveform is pulse width modulation, as you all know. That's how we generate the desired effect on the motor winding using a variable frequency drive. That pulse width modulation is pulse, 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 pulse. It's not a smooth sine wave. It therefore makes sense that we might want to consider using a special cable to handle the different waveform. And we're going to present a case to you today why that should be classified as better and sometimes even best practice versus using standard cables. Now, I don't know that a lot of people still just throw THHN in a conduit, let alone THHN for the power leads and your control leads in the same conduit. I think we're kind of getting the message across on that in the last 40 years. You don't want to run your control cables with your power cables. Shielding and separation is the rule. But how many people do you know in your customer base that are actually aware of the fact that there is an entirely different class of cables specifically designed for pulse width modulation that further ameliorates the effects, the negative effects, of the pulse width modulated waveform? And that's far less. So today, we want to create a case so that you can make a decision as to whether you want to promote this technology when using a variable frequency drive. Why wouldn't we just use this? Well, of course, it's cost. These cables can be, and this is where I would have loved to have Chris Keller because he knows the costing on these things, but I'm going to estimate that these cable costs are going to be 1.2 to 1.5 times the cost of normal cable, which, by the way, if you have a problem and you delay your installation by a day or two because you can't solve the problem, and I'll talk about the trip I made to Mexico in a second, then that cost is immediately justified. So let's move on to a video that just specifically talks about why.
Hi, my name is Christine, and I'm here to interview Stefan Grunwald, who's the Global Product Manager for Lutz's cable business, on why you should use VFD cable for motors being controlled by VFDs. Hi, Stefan.
Hi, Christine. Good to see you.
So you've created the Lucid DriveFlex product line specifically designed for VFD cable applications. What gave you this idea to create a cable for VFD applications?
Well, that's a great question. We found out that many of our customers are using power tray cable that was not initially designed to be used with VFDs, but it fulfills current code. The more I talked to these customers, the more I realized that the conversion, the power conversion inside the VFD causes some electrical challenges to those cables. And the more we looked into it, the more we found out that it's really about the type of insulation. PHHN, or known as PVC nylon, it's not very safe, can oftentimes not cope with the electrical challenges that are caused by the power conversion inside the VFD.
Can you elaborate a little more on the electrical challenges that you just mentioned?
Yes, there are three main challenges. Let me use the whiteboard to explain. The first one is the cable capacitance, or in other words, the amount of current that is required to charge the cable before I transfer any current that can be consumed by the motor. The longer the cable, the higher the cable charging current. This extra charging current makes the VFD work harder and creates nothing but heat. To avoid this major problem, you want a cable that offers you low capacitance values. This is the first rule for any good VFD cable. The second problem is the cable impedance and the motor impedance being mismatched. In a sense, this is like a bottleneck causing a slugfest. The impedance mismatch is partially responsible for the so-called reflective wave phenomenon that in turn creates a lot of electrical problems and can lead to common mode noise and motor failure. The third problem is the presence of high voltage spikes, which are a result of the internal power conversion and frequency using a process called pulse modulation. This is typical for most VFDs today, and it basically means that your output voltage from the VFD is much higher than the input voltage, and that you can have a series of voltage spikes caused by the frequency conversion. As a result, your cable must withstand a lot higher voltages than you may have expected. We have seen spikes on a 480 volt drive reaching 1200 volts on the motor. For this reason, you want a thermoset insulation material that can withstand nominal voltages of at least 1000 volt.
The voltage spikes that I was seeing in the field exceeded 2400 volts on a 460 volt system. Very long motor lead lengths, by the way. That 1200 volt is actually a conservative statement. And in fact, the latest National Electric Code specification, MG1, MG motor generators, parts 30 and 31 specify that motor insulation, not the VFD cable, motor insulation must be able to withstand 1400 volt spikes on a 460 volt system in order to classify the motor as an inverter duty motor or VFD duty motor. The other part of that specification says drive manufacturers may not produce more than 1400 volts on the output of their VFDs. That's not hard for the VFD people to do technically. It does add some cost because what we have to do is we have to slow the rise time on the pulse, on each pulse. Every one of the pulses that we put out there, and we put anywhere from 2,000 to 10,000 pulses per second out there. We have to slow the rise time on that pulse and therefore limit the overshoot, which causes voltages as high as 2,000, 2,500 to be out there. What that does is it causes more heating in the transistor because the transistor can't transition from zero to full as fast as it would like. And it increases what's called switching losses, the time when the transistor is in transition. And therefore we have to upsize our transistors. Responsible VFD companies do that. There are a lot of drives coming in that don't comply to these standards, and they don't do that. That's one of the differences, by the way, as a little side note, between the quality people that make drives, the Yaskawas, the Siemens, the ABBs, Danfosses of the world, and the drives coming in from a manufacturer that you may not recognize that is not compliant to the NEMA MG1 Part 30 and 31 specifications, and therefore is using a one-size-down transistor, but switching it on very fast. And I have seen a lot of drives come in with that type of switching. It allows them to be less expensive. So when you run up against a drive that's 70% of the cost of what you're specifying, this is one of the reasons. The fact is that this cable can help in both of those cases, certainly in the case where that drive is non-compliant to NEMA MG1 and is putting out high voltage spikes to the line.
For an extended time. PVC insulation is just a bad choice from a voltage standpoint, and that's why we have switched all our VFD cable to XLPE, which is simply a much better insulation and safer for use with VFDs compared to PVC or THHN-based wiring.
This is very interesting. Do you have any other reasons?
I want to make a clarification here. PVC is still great for the jacket of the cable. What he's talking about is the individual wrap on each conductor. They've gone to cross-linked polyethylene, XLPE. That material, an insulator, versus PVC, also an insulator, allows the cable to be designed such that it has a much lower capacitance in the cable itself. We don't want capacitance in the cable. So XLPE versus PVC, but PVC is fine to use on the outer jacket. It's tough stuff.
Why VFD cable should be used in industrial applications?
Yes, there are some other reasons. For example, VFD cable is shielded, and the shield allows you to capture and drain the noise away to ground. The other reason is there are some code and safety concerns about using THHN. THHN is a very old technology that was initially invented as building wire way before VFDs even existed. That's why when we designed our DriveFlex line, we looked for new technology, better technology installation that we feel is safer and addresses all the problems caused by the VFD.
Well, thank you very much for this interview, and thank you for explaining why we should use VFD cable.
Okay, so that is in general the why. I want to emphasize the why. These companies are not small companies. Making cable is a capital-intensive activity. You gotta have a lot of machinery, a lot of capital investment. There's a market out there for this, obviously. And you have to ask yourself, if you're still using THHN, which, as the gentleman said, was originally designed as building wire for non-industrial applications, and you're using it on a severe industrial application, a pulse width modulated VFD, intuitively, I hope that doesn't make sense to you, because it doesn't make sense. Now, we're going to talk about two more subjects before we move on from the videos. One is the impedance and one is the capacitance. So this will bring you into a little bit more detail on the technical side of why we talk about impedance and capacitance in cables. So we'll talk about impedance first.
What is high impedance?
Whoa.
We hear this term all the time when discussing both guitar and bass gear.
All right, wrong video. There we go.
Hi, my name is Matthew Tarney, Product Market Manager for Lutza Wire and Cable, and I'm here today to talk about the importance of impedance in VFD cable. If you've watched the other videos in our DriveFlex series, you know that the electrical characteristics of VFD cable can have a very big impact on performance. Specifically, you want to look for a cable that has low capacitance and high impedance. But what is impedance exactly, and what does it mean to have high impedance? Today we'll look at that factor in a little more detail. The impedance of a drive cable affects one of the most critical factors of VFD applications, a phenomenon known as the standing or reflected wave. This is a voltage spike that occurs at the motor end of a drive cable run. On a 480 volt drive, you can see spikes as high as 1500 volts on the motor end of the cable, and cable impedance plays a big part in minimizing that effect. Let's go to the whiteboard to discuss this in a little more detail. When an electrical pulse crosses a barrier from a low impedance pathway like a cable to a higher impedance pathway like a motor terminal, the flow is disrupted and some of the waveform is reflected backwards. This reflected wave combines with incoming waveforms to cause high voltage spikes. One way to reduce this effect is to match the impedance value of the cable to the impedance value of the motor so that the energy can flow with less disruption. Because motor terminals have a high impedance value, and the cable is intended to be a low impedance pathway, when we bring the cable impedance closer to the motor impedance, less energy is reflected back. How do we make the cable impedance higher? There are two factors that go into the impedance value for drive cable. The first is the insulation material used, and the second is the relationship of the conductors to one another, the actual geometry of the cable. Lutza DriveFlex uses an XLPE thermoset type insulation. In testing, we've shown that XLPE can have an impedance value as high as 2 times that of PVC nylon insulated cable. This significantly reduces the difference between the cable impedance and the motor impedance and helps minimize the reflected wave. In addition, using an XLPE or thermoset insulated material for your insulation also increases the voltage withstand of the cable, so that when you do have those high voltage spikes on the motor end, the cable insulation is up to the task.
Now, the first question you're going to get from your customer is, wait a minute, why do I want to use high impedance on a cable? The whole purpose of the cable is to be a low impedance pathway. Well, the answer to that is, if you have a circuit and you want to know the flow on that circuit, the point of most resistance or impedance is going to determine that flow. It's a serial situation. So you can have low flow up to, or low impedance up to a point, and then you have high impedance like the motor winding, and that is going to limit the total flow. So having low impedance cable going into a high impedance motor winding actually isn't a good thing. It doesn't improve the flow because the high impedance determines the total impedance of the circuit. Therefore, eliminating that difference between the low impedance cable and the high impedance motor winding makes sense. We're not creating a negative situation by increasing the total impedance of the circuit. All we're doing is smoothing out a big bump that causes the reflected wave phenomenon.
Whether you are adding a drive to an existing application or retrofitting a motor to have a VFD attached, don't forget the cable. Make sure to specify a cable with high impedance and low capacitance.
Now let's look at the capacitance side of the question. And by the way, driveflex.com, easy to remember. I recommend that you go here and you review these if the subject is important to you. And if you're specifying VFDs, it's important to understand this issue. It's a great quick review. I do it often just to make sure that I'm conversant on the subject.
Hi, I'm Stefan.
And I'm Matt. And today we're here to talk about capacitance in VFD cable.
We brought one of our DriveFlex VFD cables with XLP insulation.
And when we talk about cable capacitance, what we mean is the ability of this cable to store an electric charge. So think of this cable like this tube here.
So we have some props that will help you understand how capacitance works. This is the energy coming from your drive.
So as you turn the drive on, that energy, or this blue liquid, has to fill up the hose before it's available at the motor end to turn the load. And this requires quite a bit of energy output from the drive, depending on your cable.
Usually, you would solve that problem by going to a bigger drive.
One thing that people often don't consider is that you can also solve that problem and stay at a smaller drive size by going with a low capacitance cable. Our XLPE insulation has been shown to be 4 times less charging current than a PVC nylon insulation. That saves you a lot of energy on your drive output.
So that is basically taking the energy and putting it right to your motor.
It drastically cuts down on the energy that you lose as heat and makes your drive system much more efficient.
Okay, so that's the impedance and the capacitance issue on the output cable for Lutze. I want to also...
If you're a web designer,
all right, I keep clicking on the wrong thing here. I also want to talk a little bit, actually I'm going to go to my other presentation. I want to talk a little bit about the characteristics of the cable from the standpoint of shield as well. This I will send to you after the class today. This is something we made up. Actually, we made it up in 2022, March 23rd. And this is a best practices presentation. I want to show you some of the discussion that we had on cables. Now, I highly recommend when you use shielded cable, you're going to the expense of shielded cable anyway. You're now acknowledging the fact that a standard cable doesn't work for your application, whether it's on the output of a motor for motor power leads or whether you're using it to protect sensitive signals on your low voltage control leads. You're acknowledging that you need a shielded cable. Now use a good shielded cable. And the best thing that I can say to you is use a double shielded cable. This cable has 2 shields. One is a foil, one is a mesh. That mesh has a lot more surface area per linear inch than the foil. Why use both? Well, the foil carries low frequency signals better. Remember I said the high stranded cable, like the Lutze power cable, that welding type cable, has a lot of surface area to carry the high frequency noise because the high frequency noise runs on the surface of the conductor. So if you want to put shielding in there and you only put foil shielding, you're not optimizing the path to ground for the high frequency noise. What is VFD output? It's high frequency noise. So having both gives you a broader range of frequencies that you can effectively sync to ground on a low impedance path. You want all that noise to go to ground. You don't want it to go affect other parts of your system. So a braided shield and a foil shield, and then ideally twisted pairs for your communication or control. This may be your analog signal, plus or minus 10 volts or 4 to 20 milliamps, within an individual shield of foil and then a total shield of mesh. This is the best. Twisted pair, double shield. This, you get credit for that effort, but you don't get full credit, and you're going to get some problems on that you would not have using this technology. I recommend this on the power leads as well. It makes sense to shield your power leads because now you're suppressing the noise at the source. You're not waiting for it to get out all over hell's half acre and affect all the conductors that you then individually protect. Why not protect both? Okay, now let's talk a little bit about how you ground the shield. That's so important. Quite simply, this is how you ground the shield. And this doesn't look like what most people do, especially in the United States. Remember, this manufacturer of this cable went through a lot of effort to design the impedance path of his shields so that they're low impedance so I can sync all that noise to ground. When I disrupt his design, I change the impedance path. Here, I'm not disrupting his design. All I did is I stripped off the outer jacket, exposing the internal shield, and now I clamp it with a known force and a known surface area to the common or ground. All this hardware is manufactured to make this very easy, and this is not expensive. There's a special tool used for stripping that cable. It allows you to make a cut here, and then turn the tool sideways and strip off that 1 inch of insulation, not disturbing what's inside, allowing you to do this. What do we normally do? Well, unfortunately, we normally do this. And this is our drain line and our shield, and it doesn't look like it is in the original design of the cable. In many cases, guys will twist it up and then put a heat shield on it for neatness and then put a nice terminal at the end of it. Unfortunately, when you twist up the shield, you change its impedance. You actually increase it. You trap more high frequency noise on the shield itself. Energy is going to go somewhere. When you trap that noise on the shield, you create the ability for the shield to have a capacitive discharge. This is a diagram of inductance between two cables. Here I have a sensor, and here I have another conductor with some current going through it. There's a capacitance between the two. When that capacitance builds up enough that it can bridge across, it creates a capacitive discharge. That capacitive discharge looks like this on an oscilloscope. Sorry, that's not it. Where's my capacitive discharge picture? Sorry, I can't find that picture. Didn't I put that in this? At any rate, a capacitive discharge, let me do this. That's easy to do. Go to good old Google. Capacitive day on Google, it didn't give me the right image that I'm looking for. Let's see, bear with me just one second, because I really want to show you what this looks like. That energy has to go somewhere, and if you're not sinking it to ground, it's going to go across conductors. Didn't spell it right. Didn't spell it right. Why are you not giving me the picture I want? Well, I'm sorry I can't find you a picture of capacitive discharge, but what it looks like is a waveform that is running static, and then when the discharge occurs, you get this kind of thing going on, and it eventually goes back towards flatline again. But that point where the discharge occurs, there's a lot of energy that's discharged, and I'm sorry, I can't find that. This is talking about it, where the capacitance jumps between two conductors. Anyway, we have to move on here. Oh, wait a minute. Ha! That's weird. That's capacitive discharge. Where'd that come from? At any rate, here what you have, this is the point of discharge. Ba-bam, lots of energy. And of course, it'll dissipate as the capacitive discharge moves on in time, because that energy expresses itself. And eventually you get down to the point where you're flatline again, which is where you want to be. This point here, there's a lot of energy moving between the 2 points of the capacitor. You want one of them to be ground so that it all drains away. But if it's between two conductors, then, as it would be in this case, this case where we're unshielded, this capacitance goes to another conductor. So capacitive discharge occurs when you trap high frequency noise on a shield. It occurs when we have bad practice in terms of how we land our shields. Here's another thing I want to point out. Look at how much exposure these conductors have. These are your two analog conductors. They're right next to the motor T leads. There's all sorts of pulse width modulation broadcasting off of this. Using this method, note the shield travels on past the ground point. This can be at the point of entry in your cabinet. It can also be right at the VFD, where you mount this neat little convenience device with a proper clamp. Now, this is not good practice in my opinion, but, and I'll say it, I'll let you know in a second why. But here we have a convenient point, strip the cable, clamp it. Now extend this shield all the way up to the terminals. That allows you to extend the shield. You don't have to end the shield here. You expose it, clamp it, and continue the shield on undisturbed. So that when we go back to this example here, these would still be shielded, because I'd be shielded right up to here. It makes a big difference in the amount of noise. You want to know how much of a difference? Put a scope on these two leads and try different methods of wiring. I've done that. There's a big difference. Now, in the last few minutes, to drive this point home, I want to relate to you an experience that I had quite recently. I was traveling to the Petroleum Mexico, Pemex, refinery in Tula de Allende a couple of weeks ago. And Tula de Allende is a company town that is sort of located next to this gigantic refinery complex. I mean, this place is huge. There's flares everywhere. It looks like something out of Dante's Hell. And it's about 50 miles north of Mexico City's international airport. So my colleague Dan Comans and I flew into Mexico City, drove the 50 miles from Mexico City International Airport to Tula de Allende. On the way out there on Sunday evening, we got lost. Took us 2.5 hours to cover the 50 miles, and Mexico's roads are not exactly the greatest, especially for a couple of guys from the States who are not used to them. By the way, speed control in Mexico is unique. They don't have a lot of cops with radar. That's expensive. What they have are the biggest speed bumps you've ever seen. These things are 12 to 18 inches off the ground. I mean, they're huge. You go over those at speed, it's going to take the underside of your car off. It's kind of like the price you pay for speeding in Mexico. So you can imagine that our progress, once we got off the tollways, was very slow, because you go 30 miles an hour, and then you go 5 miles an hour, and then you go 30 miles an hour, and then you go 5 miles an hour. And by the way, there's no signs. These things just pop up on the road. So speed control of a different culture. I want to show you some pictures. This facility was nothing less than amazing. These are coking towers, and inside there are cylinders, giant cylinders, and in those cylinders they grow coke. Coke is like a high energy version of charcoal. And once the coke fills up the cylinder, these towers have winches on them that lower a water jet cutter into the cylinder. First, they lower the water jet cutter into the top of the cylinder with the water jet pointed down, and the water jet drills a hole all the way down the center of the coking tower. The process is called decoking because you're taking the coke out of the cylinder. Once you get to the bottom, this water jet then turns 90 degrees. We're controlling the position of this water jet I'll tell you how we did it in a second. And then it rotates and cuts the coke out of the inside of the cylinder. It drops onto this giant conveyor. There's the end of the conveyor, and it takes it away to the trains. In some decoking facilities I've been in, they drop the coke right into the cars of the train. It's a byproduct of the refinery process that actually is sold to good effect. Coke is used in blast furnaces to make high quality steel. The electric arc furnaces that produce steel are more efficient, but you can't produce high quality automotive body sheet metal in an electric arc furnace. You need coke to create it in a blast furnace. So still a very important process. Now, we did the winches that carry the water jet up and down. We also did the motion on the rotary joint, which is where we divert the water to the direction that we want. That was a very interesting application because we didn't have a lot of room. And what we did is we stuck a Yaskawa servo motor on the rotary joint that turns the water jet around 360 degrees. And the rotary joint itself is very interesting because obviously there's a seal there that allows the water to turn 90 degrees and go out the jet. To give you an idea of the pressures involved here, the pump that's producing the pressure on the water that's going all the way up and down inside this decoking tower and out of this rotary joint is a 5,000 horsepower motor. A lot of pressure, which you would need obviously to cut coke out of the inside of the tank. The rotary joint is a standard VFD. In this case, it was an A1000 because the system was originally designed in 2016 before the GA800 came out. It's an A1000 open loop running a PM Yaskawa servo motor, a Sigma 3 servo motor. It's a great application because we've got the thing in there, Yaskawa's motor's IP67. Can you imagine? We put a Yaskawa servo motor inside a decoking tower and it's surviving. Talk about good quality product. So the winch itself is a big induction motor, with an encoder on it. We're running that closed loop. And that's the application I want to talk about. The system was designed in 2016 for a variety of reasons. It didn't get installed into this year. I don't even want to go into that. But when it did get installed, they turned the drives on, and the drives on the winch immediately overcurrent tripped. Bang, OC trip. And they couldn't get it. They couldn't figure it out. When I arrived on site, I was told a couple of very interesting things. One, the distance from the decoking tower to where the drives were installed wasn't 175 feet as we were told in the original specification. It was 600 to 900 meters. And that just totally changed the whole characteristic of the tank circuit between the VFD and the motors. We're talking about lead lengths that we had no expectation of. We don't have a lot of time, so I'm going to short circuit this story. This is where all of the VFDs were. That's my colleague Dan Comans. He's not very happy because when we arrived on, when we came out of the hotel on Monday morning at 6 a.m., they looked at us and said, put on these orange jumpsuits. Everybody in this place wears orange jumpsuits. It looks like a giant penitentiary to me because people in our country wear orange jumpsuits and when they go to jail. But they told Dan, you have to shave your face. Dan had a goatee, and Dan had to shave his face because in a petroleum facility, you're not allowed to have facial hair because if they have to put a mask on you, it leaks. But anyway, there's Dan. He's not very happy. This is the gigantic. This thing is 3 football fields long. There's that many MCCs in this thing. The Square D guy made out like a bandit because, oh my God, there was so much Square D equipment in there. But that was 600 to 900 meters away from this. They couldn't even tell me the exact distance because obviously the conduit goes up and down and around to get to the motors up top. The motors, and by the way, there's an encoder signal coming back, right? So let's deal with the encoder signal first. Let me see what this is. Oh, that's the capacitive discharge that we saw on the scope. Here's the encoder signal coming back over that length of leads. Sorry. I was amazed. That's a pretty good signal. Let me do it again. There's your A and your B with the differentiation in phase between the A and the B to tell which direction you're going. So, not a bad quality signal. How did they do that over such a long lead length? Well, they used a fiber optic link. So these guys actually were pretty good engineers. They had the fiber optic link between that covered the majority of the 600 to 900 meters. And I'm going to tell you that when I first heard it, I thought, propagation delay. Is this going to be out of phase? Is the motor going to be able to be commutated by the VFD? There was no propagation delay to speak of. The signal quality, as you saw, was pretty doggone good. And now I realize I can use a fiber optic link on long encoder lead lengths and still maintain the ability to commutate, where the timing of the pulse is extremely important because I got the pulse timing coming from the encoder all the way over the lead lengths back to the VFD. VFD processes it, then starts changing its PWM output according to the encoder feedback. That loop cannot be a long period of time. That's got to be measured in small numbers of milliseconds. And the fiber optic link did a great job. Now, what about those long motor lead lengths and that tank circuit and the change in capacitance and impedance associated with that circuit? Why were those drives immediately over current tripping? By the way, when they ran it in open loop, we didn't have tripping on the permanent magnet motor, and I haven't figured that one out yet. But what we had on the output of this drive was a standard PCI EVDT filter, which is a reactor with phase-to-phase capacitance. This is a capacitor that is associated with this filter. It's held in there because we removed it. That capacitor, which was fine in the motor lead lengths up to 175 feet in the original design because we tested it, became a real problem for the drive when we increased the lead lengths out to 900 meters or 600 meters. And we had to remove that capacitor. When we removed the capacitor, the problem went away and the drive did not OC trip. So that's one of the reasons why long lead lengths can affect you. And they didn't use inverter duty cable like we had specified. So the whole tank circuit changed. My point in telling you this is when they paid us an ungodly amount of money to go down there. We didn't want to go down there. The point is that they failed to realize that the output characteristics associated with the tank circuit that we've talked about for this entire class, this is real. This isn't some salesperson trying to sell you VFD cable that you don't need. This tank circuit is a real law of physics situation. It has to be dealt with. If not, you've got consequences like I'm illustrating to you here. By the way, as a final denouement, there's the encoders that we use. These are nice encoders, by the way, these Dynapar HS35 encoders. It's a 1-inch shaft on the tail end of the winch motor. It tells you how big the winch motor is because that's just the stub shaft for the encoder. These are standard quadrature line driver, 12-volt signals carried over 600 meters by a fiber optic link. I'm still amazed about that. I've been in this business a long time. It just goes to show you, you learn something every day. However, these encoders were in the weather. So we're shipping them new encoders that are IP67. They also have to be class 1 div 2 because it's an explosive area. But yeah, that caused some problems too. So anyway, I hope we've made a case for you to consider the output characteristics of the VFD to the motor called the tank circuit, the impedance, the capacitance, and the tools like special cable that you use to make that circuit perform correctly. Thank you very much. It's 8:05. Time to go to work, and I won't see you next week because I will be on vacation, but one of my colleagues will be teaching the class next week, and the following week, I'll be back the week after that. Thank you very much, and have a great day.
Thank you.
Thank you, Pierce.
Bye for now.